Okay, so for vertical compressions and stretches, the thing that was shown on the previous slide was that what we really, and there was a typo on the previous slide, so be careful. If we're multiplying after the action of the function by a number that's greater than 1, then it grows all the y values, which stretches the graph. But if we multiply by something like 1/2 or something that's between 0 and 1, then it's going to compress the graph by making all of the y values smaller. So we're going to examine that by looking at the square root function. First, we're going to take a look at a vertical stretch, and we're going to do the square root function multiplied by 5 on the outside. So the first thing to keep in mind is that you can still rely on your table, but we should make a note that 5 is in this category of being bigger than 1. So we already have a prediction that it's going to stretch it out so it looks kind of taller, is how you might think about that. So the ones I like to plug in will not change. I'm going to do, let's see, we'll get rid of this. We're going to do 0, 1, and 4, and then I'm still going to get that 0, 1, and 2, but then by multiplying the outside of that by 5, I get 0, 5, and 10. So my vertical stretch looks like, instead of being at my original function, which I will do in blue, which was 0, and then I go 1, 1, and then 1, 2, 3, 4, up 2. This is my original square root function. I'm going to instead go ahead and graph my 5 square root of x, which will have the values 0, 0, 1, 5, and then 4, 10. Because remember, the middle is just kind of to help us out. It's not part of what we graph. So 0, 0 is the same. 1, 1, 2, 3, 4, 5. And then 4 will be up at 6, 7, 8, 9, 10. So you can see it kind of spikes it up. Really what I've done is I've stretched it vertically, okay? And a vertical compression, an example of that would be like 1/4 square root of x. And I can do it with a table. So I start out the same way for both of these, 0, 1, 4, 0, 1, 2, and then 1/4 of that would be 0, 1/4, and then 2/4, which is 1/2. So if we graph that on that same picture, let's make this one in green. So I'm going to plot 0, 0, 1, 1/4, and 4, 1/2. So 0, 0 is still here. 1, 1/4 is going to be really small, way down there, and then 4, 1/2 will only be over here. So you can see it's kind of been squashed. It still should have the shape of the other one, but it'll be squashed. And the other thing to note here is, like, what if it's a negative number, like -5 or -1/4? Then you would still graph this to begin with like this, except then all the points would be reflected across the x-axis. So it would flip it over. This is similar to what we were doing with the vertical stretches and vertical compressions, except as usual, we basically are saying when it's on the inside, it's going to behave the opposite of the way you expect. So if I want to do a horizontal stretch, my horizontal stretch isn't going to have a number in here that looks like it's going to make things bigger, right? It's going to have something between 0 and 1, because horizontal behaves opposite of what you'd expect. And if I want a horizontal compression, then it's going to be something that looks like it's going to make things bigger, right? So because it's on the inside, it behaves the opposite of how you expect. So again, for this one, I like to always begin in the middle for all the horizontal ones. The thing I want to put under the square root is 1/4 x. That's what I'm going to take the square root of. So I want those to be my nice numbers to use. And so if I want to trace that back to what x value it came from, I'm going to multiply each of those by 4. So I picture take x, do a fourth of it, now take the square root of that. So take x, like x is 4, do 1/4 of it, you get 1, do the square root of that. Take x is 16, do 1/4 of it, get 4, do the square root of that, get 2. And we end up with nice numbers, and it looks like the x value is 0, y value is 0, x is 4, y is 1, x is 16, y is 2. So from here, I can end up with kind of a long graph, right? So this ends up being 5, 10, 15. I'm at 0, 0, 4, 1, and then 16, 2. And I don't have my original graph on there. It's honestly going to look a little bit funny if I don't kind of keep going. Let me see. I might plot a few of them. So it would still be 0, 0, but then it would be 1, 1. And then it would be, 4, 2. And then by the time it got up to 16, which that last dot kind of honestly looks like a 15. We're going to slide it over. How about that? By the time I get up to 16, I'm actually going to be up at height 4. So this would be my like square root of x, and this would be my square root of 1/4 x. So it is a horizontal stretch. And my other one, my horizontal compression, is going to be, again, start from the middle. Those are the ones we like. We want to make sure we put ones that we actually want to take the square root of there. So that came from dividing each of these by 4 to go back. So if I plug 0 into my function, I get 4 times 0 is 0, square root of 0 is 0. If I plug 1/4 in, I get 4 times 1/4 is 1, square root of that is 1. And if I plug 1 in, I get 1 times 4 is 4, square root of that is 2. So 0, 0, 1/4, 1, 1, 2, which on the graph would look like, it makes it look like it's spiking up sooner, right? So I plug in 1 and I go up 2. So it's going up way more. Whereas my previous graph would have been, 0, 0, 1, 1, 4, 2. So horizontal compression kind of squashes it in, and a horizontal stretch kind of pulls it stretched out wider. And again, if it's a negative, then it's going to have a reflection as well, but this time it would be a horizontal reflection. So if the number on the inside is negative, it's going to flip it over the y-axis, which would look like, if I did something like the one I just have here below, if I make that a negative, it would be like this, but with, sorry, I should make it matching the black one, but up, right? So you can also fix your table for that, but that would do the trick. All right, so for this slide, I just want to talk about the fact that there's not a unique way of identifying what's happening to a function. So for example, for this one right here, I could also think of this as being 2 squared x squared, which is the same thing as y equals 4x squared. So when we have this factor of 2 on the inside, that means we have a horizontal, and let's be careful here. You want to make it a stretch because it's 2 and 2 is bigger than 1, but it's actually a compression, okay? And if we want to get into a little bit more detail, like what are we compressed by? It's actually compressed by, and this is in the previous slide, it's compressed by 1/2 for this one. And for this one, this is a vertical stretch by 4. But if we look at the graph, the original function looks like, your squaring function, like this. And then when we graph this one, we end up with, I should have probably gone a little higher, but it spikes up more. So it still is at 0, 0, but if I plug in like 1, I'm gonna get all the way up to 4 right away. And so you can picture this both as a vertical stretch or as a horizontal compression. So there's not, in this particular function, a unique way to describe it, but there are functions where there is only one correct way to describe it.